Today, we're going to get into the story of how AI basically grew a pair of eyes and ears. This is really a tale of two different kinds of networks, the absolute workhorses behind things like your phone's camera recognizing your face or your smart assistant actually understanding what you're saying. It's all about two revolutionary ideas that taught machines to make sense of the world in ways we used to think were, uniquely human.
And it all really comes down to this one massive question. See, looking at a picture and reading a sentence, they're just completely different animals. An image is this giant grid of pixels, where everything is about spatial relationships. What's next to what? But language, that's a sequence, where order and context are everything. So you can't just use the same tool for both jobs.
And this slide right here, it just nails the problem. Over on the left, you've got spatial data, an image. The meaning comes from how all those pixels are arranged. On the right, you've got sequential data, a sentence. The meaning comes from the order of the words. If you scrambled the pixels on the left or the words on the right, you'd completely destroy the information. So how on earth did AI figure out how to solve these two totally different puzzles?
All right, so let's jump into the first hero of our story, the convolutional neural network, or CNN for short. This is the architecture that, for all intents and purposes, gave computers vision.
Before CNNs came along, trying to get a regular neural network to understand a picture was, it was a total nightmare. A standard network tries to connect every single input to every single output. For a modern high-res image, we're talking billions, maybe even trillions of connections. It's just wildly inefficient. And even worse, it has zero built-in sense of space. It just sees a giant, flat, meaningless list of numbers.
So the big idea, the genius move, came from this really elegant mathematical concept called convolution. Basically, you have this small filter. They call it a kernel that just slides across the image. The best way to picture this kernel is like a tiny, specialized magnifying glass. It's not looking at the whole picture. It's just trained to spot one very specific thing, like a vertical edge, a little curve, or a certain texture.
And here you can actually see it in action. That little kernel slides over a patch of the input, does a quick calculation, and then spits out a single number in the output grid. When it's done scanning the whole thing, you get what's called a feature map. Think of it like a treasure map that only highlights one specific thing, like X marks the spot for every single vertical line it found.
Now, this whole convolution approach gives CNNs three incredible superpowers. We're going to focus on the first two here, sparse interactions and parameter sharing, because they are the real game changers that made all of modern computer vision even possible.
So first up is sparse interactions. Remember that old network where every single thing was connected to every single other thing? A total mess, right? Well, CNNs don't do that. Here, each little neuron in our feature map is only connected to that small, local patch of the input that the kernel just passed over. This just massively cuts down on the number of connections and calculations, making the whole system way faster and more manageable.
The second idea, and this one is just brilliant, is parameter sharing. Here's the key. The network learns one kernel to detect, let's say, a cat's ear. Then it uses that exact same kernel everywhere across the entire image. It doesn't need a separate top left cat ear detector and a bottom right cat ear detector. No, it learns the concept of cat ear once, and then it can find it anywhere. This is monumentally, ridiculously efficient.
Okay, the last piece of the CNN puzzle is something called pooling. After the network makes all those cool feature maps, it simplifies them. Imagine you're just squinting at the map. You don't care about the tiny exact details. You just want to know the most important or the strongest signal in a little region. That's pooling. And it has this fantastic side effect. The network starts to care less about a feature's exact location. It doesn't matter if the cat's ear is on pixel 57 or 58. Pooling just says, yep, there's definitely an ear somewhere around here. This gives the network a really robust way of seeing things.
Okay, so that's how we gave AI eyes. Pretty cool, right? But what about language? For that, we need to move on to the second part of our story and meet the recurrent neural network, or RNN.
Language or speech or even stock prices, they aren't static grids of pixels. They're a flow. The meaning of a word depends entirely on what came before it and what might come next. A CNN is completely blind to that kind of structure. So we needed a totally new kind of network, one that was built from the ground up to understand sequences.
And the core idea behind the RNN is actually super intuitive. It has a loop. So when it processes one thing in a sequence, like one word in a sentence, it produces an output, and then it feeds a little piece of that information right back into itself for the next step. This feedback loop acts as a kind of memory, giving the network context from what it just saw.
And don't worry about all the formulas here. Just look at the diagram on the left.
See that looping arrow? That's it. That is the entire magic of an RNN. It means the network state at any given moment depends on both the new word it's looking at and what it was just thinking about a moment ago. It's constantly updating its own understanding as it reads through a sentence.
Now, if we unfold that loop over time, you get the diagram on the right. This makes it super clear what's going on. The network processes the first word, passes its memory, that little h, to the next step, then it processes the second word, plus that memory from the first word, and on it goes. It's the same network, the same logic, just applied over and over again for each step in the sequence.
But this simple design had a pretty major flaw. I mean, it had memory, sure, but it wasn't very good at remembering things for a long time. It was kind of forgetful.
So, imagine you're reading a really long paragraph, and the main character is mentioned right in the first sentence. Well, by the time a simple RNN gets to the last sentence, the influence of that first crucial piece of information has pretty much faded away. It gets washed out by everything that came in between. This is what's known as the problem of long-term dependencies.
And the solution was an absolutely brilliant upgrade called the Long Short-Term Memory Network, or LSTM. It's still an RNA at heart, but it has a much more sophisticated internal structure. Instead of just a simple loop, it has this complex memory cell with a series of gates that act like tiny, intelligent gatekeepers for information. The way these gates work is the crucial part. So the LSTM has a forget gate that literally learns when to throw out old, irrelevant information. Then it has an input gate that decides what new information is important enough to save to its long-term memory. And finally, an output gate decides which part of that memory is actually useful for the task at hand. It's this incredible system for reading, writing, and erasing information that gives it a powerful and really durable memory.
So there you have it. We have these two powerhouse architectures, one that conquered the world of space and another that mastered the dimension of time.
Let's just put it all together real quick. On one side, you've got your CNNs. Their domain is space, grid-like data, like images. Their core tricks are convolution and pooling, and they solve the problem of seeing patterns. On the other side, you have RNNs, especially those powerful LSTMs. Their domain is time or sequences, things like text and speech. Their core ideas are that feedback loop and those memory gates, and they solve the problem of remembering context.
And this leads us to the final and maybe most exciting thought. These two networks aren't just powerful on their own. The real magic, where AI really took a leap forward, was when researchers started plugging them together. Imagine a network that can see an image, feeding its understanding to a network that can remember and put that understanding into words. This fusion is the foundation for modern marvels like generating captions for images or analyzing videos. It just goes to show that in AI, just like in life, the most amazing things happen when different ways of understanding the world finally come together.